Okay, so just to like review some data modeling, because I did see it come up a little bit. Sorry. All right, so yeah, so just to review some data modeling stuff. Okay, say we have like this artists and songs stuff, right? And you could think, okay, so like an artist has many songs, I would think, right? In terms of where to store the ID, I know this may feel like really review to you, but they're like how to link these two things, right? We know we need a foreign key somewhere. If you put, let's think about it. If I put the song here, like I want to link, Purple Rain to Prince, so I'll put the song ID, right? And then I say, okay, well that's one. Well, that's problematic, right? Because, well, now I'm basically saying Prince only has one song, right? And you could say, well, okay, well, what if we then just create new rows? Well, the problem with that, so now I'm like, okay, well, he also wrote When Doves Cry, but now I'm repeating all this information, right? So that's our issue. Okay? So instead we say, okay, at least for this purpose, we'll say a song has just one artist. So that's why we can put the artist ID here, right? And then we say, okay, well that's Prince, and that's Prince, and that's Paul Simon. Okay? And you can start, like, if you actually write out the rows, right? Like actually give yourself some examples. It's good because then you'll see the problem. You'll be like, oh, wait a second, I'm seeing Prince, twice. That's bad news. So delete this. All right. So we have our, man, that was weird. We have, so we have a song has just, belongs to one artist. If you said a song has many artists, right, how would you do that? Well, now you have a many-to-many relationship, right? Because an artist has many songs and a song has many artists, right? So let's say there's like, Paul McCartney. Is it McCartney? I forget it always. McCartney, right? And then John Lennon, right? So a song has many artists, but then what do we need? We can't stick the foreign key on either table, right? Because once we put a foreign key there, we're just saying there's only one. So now you need the join table, right? So here you'd have the song, I don't know what you call this, like, it must be a word, like attribute, not attribute, like a credit or something, maybe like credits, and that would have like a song ID and an artist ID, right? And let's say that was like She Loves You, or whatever it's called, right? And that's number 5. So that would be, we would say Paul did that, and then also John did that. Okay? Because we would have an issue, right? If I couldn't stick that here, because then I'm just saying, well, an artist just has one song, and I also can't stick it here because maybe there's more than one artist that writes each individual song. Maybe there's like 5 artists, right? So in that case, we move to our many-to-many, and we say, okay, we just have this third table. And that's really all the relationships we have, is like one-to-many, an artist has many songs, or a many-to-many, where an artist has many songs and a song has many artists. All right? One other thing to point out, right, like while I was kind of drawing this out, you start to realize other things being coupled together, right? Like you notice a repetition of like Purple Rain. And you also probably notice the repetition of like year, right? So this is like a hint that these two things probably go together, which makes sense. And then you confirm it with like logic, and that makes sense, right? Like these songs all debuted maybe on the same album, obviously at the same time. So that, then you just have an albums table, right? We'd have 1, 2, 3, the name, ID, the name, and the year, right? And then, we just move that over here. Right, and now you can collapse this. and just put an album ID. Okay? So, as you see the repetition, again, it's like repetition across multiple columns. You start to think of ways to get rid of that. Okay? So it's the same thing, give yourself an example, see the problem, find a solution to solve the problem. But by giving yourself your example, you'll see more issues. Questions about this component? All right, let's do the problem, the theater's problem. So for that, it's like, what's the transaction, right? Or what's the event? Now, that you're starting with. In this, I would say it's like either a ticket, probably like a ticket, and then you can just think of what's going on with the ticket. And you can just probably, the who, like the person ID, perhaps. And you can always revise this, but I'll start with that. The what is like the movie, and then you have the where is maybe the theater ID. The when is the time. Oopsies. Right? This is, by movie I mean like the title, like movie show. I'll just put title for now. All right, and then we can start to break this out. And maybe you say also like the seat. You could say the seat. I'm not sure, but you could do that as well. Okay. As you break this out, let's start with like the person reserves a movie to see this theater, right? See this at this time, sees this movie at this time. Well, you'll start to see, I think, as you break this out, let's do ticket. And we say we see this movie at this time in this theater, right? And this is Kindergarten Cop, which was on Netflix a little while ago. And they see this in Theater 1 at 12:30. And then you buy another ticket, right? And everyone's seeing Kindergarten Cop. So what you'll notice, right, is like this ticket thing is really like a showing. Like we're gonna have 100 of the same rows that share 3 of the same attributes, and the only thing different is like the person buying them. So what this kind of tells us is like, all right, well, there's this other entity which is like a showtime or something like that, right? And what's the showtime or showing? Well, that is, and maybe it probably would be a showtime. I like that because it feels more the parlance. So that would be an ID. That would be the actual movie ID. That would be the theater ID, right? The room ID if you don't want to confuse it with like the building. The room ID and maybe the time. Okay? Right? And now all of a sudden, to reserve a ticket, what you do is it's a ticket ID and you reserve it for a showtime ID. Right? And maybe a person does that. All right? So this would be, they see Kindergarten Cop in theater number 10 at 12:30, and here we have represented that they're seeing that movie and this guy's seeing it. All right? And then you just break stuff out. So this is the main entity that I would be looking for if I was given this question, is just seeing the repetition and then breaking it out. But there's obviously more that you could do. So let's start to do that. The main thing, I'd say there's a couple things we could do. One perhaps is to think that the movie and room go together a lot, right? Like if you walk into a movie theater, right, it's generally showing that same movie in the same room, across a day at least. So maybe you break this into a separate table, right, and just replace that with like the movie room or something like that. That's one thing to do. The other thing that we talked about perhaps is, well, maybe a person really buys. This is the same person buying 10, 20 different tickets or 5 different tickets for his family. So really maybe what you have is a purchase, and I think a good number of you all did that. And so what do we buy? This is a person ID that does the purchase, right? And this is person number 2, and they're buying it for a showtime. And maybe you have like number of tickets. I don't know. Or maybe it's the ticket number, the seat number. I'd have to think about that. So purchase, we have a person, showtime, and maybe let's just do number of seats for now. It's 3, and the showtime is 1. All right, so this individual is buying really 3 seats, and then maybe you have the ticket there. I don't know. I'd have to think about that. Maybe it does make sense. Go ahead. Oh, I thought someone was going to say something. I'm trying to think of other issues. Oh, Abhinav, go ahead.
Yeah, so we had a discussion in one of the rooms. The fact that a movie's 3D, we were debating how to capture that in this table. And so, like, do you have that as 2 different movies? Like, they have the same information, but, like, one is 3D and one isn't? Like, do you consider that 2 different movies? Or do you somehow, like, roll that into one thing? Or do you put 3D somewhere else altogether? And especially, how does that relate to price? Because, like, presumably those have different prices.
Yeah, okay.
So I just want to put any thoughts on that.
So it's, okay, what would we store? So that's kind of maybe the first thing is like, what are you storing in the movie table, right? So it's like the title, the director, right? And my guess is like price probably is not here. You know what I mean? Like, so if price was here and then you had 3D, format, right? And then you would be like, okay, well here is, Avatar, normal, right, for $10, and 3D, right, for 15. Well then, right, these 2 things are going together. But my guess actually is that the price is varying based on like time and things like that. So price actually might be more on Showtime. You start to think like, what goes together, like what is consistent, right? So for me, let's think about it. It probably wouldn't be movie. Price probably would not be stored on movie, because I could see that changing based on matinee, right, and evening.
What do you think about just not having price in the sequel table and just calculating it dynamically based on like adult or child
There's
time?
some sort of formula that does it?
Yeah.
It depends.
Because it depends on a lot of different things.
I say it depends because, like, say we were doing this for analytics purposes, well then I probably would really care, about tracking that revenue and how much we made. So I probably would do that. It also doesn't seem to me, it seems pretty consistent with Showtime, right? Like it doesn't vary it's not like it varies based on which seat you get or anything like that. Like it's not like a plane, right, where maybe you pay more for certain seats. It seems to go along with this to me. What do you think?
Thanks, but I can see that, like,
right, like you could generate,
Yeah.
you could have some sort of formula, that generates this price automatically, but
Yeah.
then storing it here, I think I don't see
Okay.
too many issues with it.
Wouldn't it go more on the ticket or the purchase? Because that's what it's about.
Well, let's think about it. If we put it on the purchase, right, what's going to happen, and you put the price here. So what you'll start to see is like, well, we're seeing the same movie at the same, like we're both seeing Avatar 3D, right? So everyone so it becomes determinative. It's like if you're seeing this movie in the evening, right? At this price, like the Avatar 3D, we know what price you're paying. And at that point, right, you get this issue of you're repeating the data, like you're repeating this amount, and you can save yourself by just storing this one place, right, which is here, right? By virtue of the fact that we're seeing, this movie, if I say we're seeing movie 2, we're paying $15 for it. That's kind of how you start to see that.
When we create the fare table, it should be the format and the price and the code should be there. I think that will be more like the.
So you have a fare table, and
it has a code, price, and the format. Is it a 3D movie? Is it a standard movie?
Yeah, but again, like I would think about what, like repeating the date, like what goes together. Right? Like price is determined. Like if I know the name of the movie that's being seen, the format and the time, I probably know the price.
Yeah, when I used to work at the movies way back when, that was like my high school job, and it was based on a format kind of with time, because like if you're seeing a movie in IMAX 3D, the matinee price was the matinee price, and IMAX had a certain tax, so it was determined based off of time, ticket type, and basically those were the two things. So if it was a standard movie at matinee, you have a set price. So you get it from like, you can have a fare table on its own that just pulls based off of time, and movie type, and that'll calculate it from there. And then from there, you can probably just sum for like movies specifically to get detailed information about ticket sales.
Yeah, one way of thinking about it is like if I give you this information, right? Like this person purchased this showtime essentially, then we can know, like there's no issues essentially with knowing what the price is going to be. Like we can look up the price and figure that out, and it should be accurate, right? Like they're in this room, with like the format's consistent, right? Like the format is kind of determined by the time and the room. Maybe and based on those attributes, we know the price. So I'm able to basically like have this one pointer, and this is not going to vary, right? This would be different, say for a flight, right? We couldn't say like, oh, well, you booked this one flight, you're paying this price. We all know that's not accurate, right? But in this case, this seems to be consistent. Like I can capture all this information and just write it down one time, the price one time, and not lose anything, by sticking it in this row. That's the way I think about this stuff, and that's the main. Right, like that's the main takeaway I would say is like, look for, okay, what goes together, like what's determined. Kind of, if I know this information, the showtime, will the price be like consistent? And so I can then, it feels like I can then capture that. I can stick that here, right? And the other way is to see the problem, right? To see, okay, we're all seeing the same showtime, and because of that, we're all seeing, the price keeps being $15, right? To me, that's like what people would say, like a code smell, right? Like something's wrong, right? If you keep seeing these things go together. What that tells you is like, oh, well, actually, I should probably move this price over to here. Let me see if there's another question. Prick ticket price type ID. That's interesting. So Brian, I don't mind. That's kind of interesting. This price type ID, because what Brian's saying. Let me just show you this idea. What I think Brian's thinking is, well, wait a second. If I tell you. If I tell you the time, and I tell you, like, the format, it's like IMAX versus 3D, right, versus standard. It's like, if I tell you this and this, I can probably tell you the price, So, so now we're breaking our rule again. So why don't we have this thing called like price type ID, right? And it probably is like a rule written down somewhere on the website or something that tells us, okay, if you have like, you know, the show time, not the time, but the like matinee or evening, I don't know what you call that, a time category, and the format, I can tell you the price, right? And so perhaps I don't know if you would combine those three things here. And probably you don't call it price type ID, but maybe you call it, I don't know, like grade, I don't know what you call it, movie grade or something like that. Person type is not accounted for either. Good point. Person type, youth, adult, senior. I like that too, right? Right, youth, adult, senior. Yeah, so you can go pretty far with this. I think of following that rule. It's like I said, you'll ask your interviewer those types of things, but I think what's good to see, and the way I do this, is you start looking to see like, all right, what goes together? Like, where do I see repetition? If you're seeing repetition among these two things, like matinee, IMAX, always means this, well then, you know, these can go together, right? Like, and then, you know, one way, and so that's why we wouldn't have it as on the ticket, because I know just by virtue of seeing the showtime, I can tell you what price it is, right? And I guess Brian would say, you know, well, not totally, right? Like, we also need to know what kind of person it is. That's fair, meaning like adult, senior, child. And so maybe you capture those few things together. But it's that logic that I want you all to start following. Like, what goes together? What am I seeing repetition across columns, right? Showtime ID and price. And then therefore, maybe you move it over here, or you could go even further and say, well, really, these three columns go together, combined with a person type, and that moves into its own table. And then you just have a pointer to that price type ID or whatever you call it, category. Yeah, I mean, it's complicated. This stuff is like, literally, you can debate this stuff over days. Let me bring about one other point that I saw come up, and that was the idea of, okay, we have like a theater ID, you know, and then, so that, let's say this is, you know, and maybe there's also like a format here. I don't know if we want to do that. Let's say there's a theater ID, and then you have seats, right? And so you have like you know, the front row, maybe you have the row and the column for seats. Okay, so we're in the first row and we're the third seat over, like J or whatever you do, right? And then we're in the first row and we're okay. Okay. The one thing I'd point out is like, when you do a reservation, if I do, let's say we have a reservations table, and you have, all right, like this is my, you know, customer ID. It would not, I don't think you can do this. You can't be like, customer 1 reserved this seat, because how long do they get the seat for? Like, when they reserve the seat, like they don't own the seat. Like, this is temporary, right? So really what you get is you get a seat for a showing, is what I would say. So there's different ways to do this. One is you could just put like the showing, or the whatever what we're calling like the showtime ID down here. So really it's this customer reserved this seat at this time, right, for this movie. Or maybe what you say is you could have like a seat availability. Like, if you think about, again, back to like the flight analogy, when you pick out your seat, we produce kind of like that map for that flight of all the seats available. And maybe, you know, you have the ID, and we say, okay, this is my seat ID, and this is the showtime ID. And then we say like the customer, if there's a customer, right? And it's null or it's a certain value. So again, it depends on how detailed, right, like the product people want. But I would not. You can't do this. You cannot. I don't think say here's the row, here's the column, and here's the customer that gets that seat, because again, it's temporary. That you're getting the seat for a showtime. That makes sense. All right. Yeah, this stuff is tricky. I don't know. But like I said, I've been asked these in interviews, and I also, generally, this is my go-to for asking when I'm giving someone a technical interview. And the main thing I'm looking to see, like, I think the first step for me is like, do you see that like this showtime, that you're, this repetition between like movie, room, and time, right? And that you're not just displaying it one for every ticket, but rather realizing this thing of showtime. If you got that far, that's quite good. And then everything else is, bonus. Right. Okay. We can shift gears now. We can talk about like Redshift a little bit, or like what the benefits of it. Okay, to do that, just to understand hardware a little bit, I forget if we've talked about this before, but really, when you think of like a computer, right, it's really just a combination of like your hard drive, your CPU, and memory, okay? So for the hard drive, that's kind of like the easiest, right? This is where we store, especially if we're, Redshift or Postgres is living on a computer. So the hard drive, that's where we're just storing data on a disk, right? CPU is actually what's running individual processes, but really when you think of a CPU, right, you can think of this chip, but what determines the number of tasks you can truly run in parallel is the number of cores, right? CORES, right? So if we have 4 cores and 2 CPUs, we can perform 8 tasks in parallel, right? And then memory is an alternative way of storing data, but so it's also used for retrieving information. And the benefit is it's faster than reading data from disk. We can talk about why at a later time when we get into like caches, but it's faster than to retrieve data from disk. The downside is one, it's only temporary. So once you shut down your computer, that memory is gone. And then the second downside is it's more expensive than storing data on your hard drive, right? So generally, like the amount of data you have stored on a hard drive is a lot bigger than the amount of data you have stored in memory. And I show this, by the way. I show like, hey, when we read, data from disk, right, it takes this amount of time, and then once we have that data, right, it takes half the amount of time. So here, when we're loading our data frame, just like displaying it, right, this is in memory. Here, we're reading it from a file, from disk, okay? All right. Now, specifically for like databases, how this interacts with our hardware is that in Postgres, when you're storing data, for the long term, right? So it can't be in memory, and it's stored on your hard drive. It must be each table. The way Postgres just is designed, every table is stored in a separate file, and each file consists of this entity called a page. Okay, and a page is just a fixed amount of space in the file. And the importance about a page is it is the smallest unit that Postgres can read. So in other words, it's never reading. It's like it's the atomic unit essentially. So if you find, if one page consists of 3 rows of data, it can't just read 1 row at a time, right? It's pulling out that entire page into memory. And the size of a page is essentially 1 paragraph of text in terms of amount of data that you're talking about. All right, like 3 sentences. So again, you're thinking like maybe like a row and a half, something like that. So that's the smallest unit. That will become important as we learn about Redshift. And then, of course, like what's actually figuring out which page to read and finding that data, that's the CPU, all right? So that is the processor. And what it will do is it will first read the data The CPU will read the data from disk into memory and then work with that data. So for example, like say we're just selecting certain columns of data, it has to again read the entire page into memory and then work with it to say, okay, really we just need to display back these specific attributes to the user. Or pull out this data and then, you know, read into memory, combine it, sort it, things like that. But, you know, first step is just read the pages from disk into memory and then operate on them while they're in memory. Okay, so that's kind of the way you can think about this part. So that's what I'm showing, you know, is like even if you only need, with standard Postgres, it's row based. So even if you only need certain attributes, like say we're only selecting user's name, the entire row, because of the way it's stored, the entire row is going to be read into memory, right? Because it's reading an entire page at a time. So that gets us into, I guess we can just skip straight here, column-based storage and why we have it. So generally, right, our transactional databases, the databases that back like a website, right, like when you go to, you know, Amazon and or Facebook or whatever, what do you care about? Like you want to buy, you know, a TV, you care about all the information about that TV, right? You know, under the price, the guy who made it, whatever. You go to like a person's profile page. You want to know everything about that person, their birthday, their whatever, you know, their photo, etc. So in other words, what you pull out is you pull out the entire row of information, right, with a transactional database when we go visit a website. That's what we want to find, is basically like an individual row most of the time, right? A tweet, right, is one, you know, the text, the time, the user, etc. With an analytical database, what do we care about? We care about generally a specific column of data, but many more rows. So we don't need to know, if I want to find out, right, like when were most movies released, or when was what's the average runtime per year, I just need two columns of data, all the rows. I don't need to know, you know, the name of the movies or the production companies, etc. So, you know, this is all going to be extra in an analytical database, right? For analytical queries, some of these columns are more likely to be extra. For a, you know, transactional database, we do care about generally the entire row of data, because when we go to an individual page, right, we want to see all the information about that user, that movie, that product. So this controls the way that we store the data, because when we pull out data, we have to pull it out a page at a time. So you can see this is how we store data in like a transactional database like Postgres. You have the row, here's Pulp Fiction, 1994, 154 minutes, made by Miramax, and then the next row of data, right? Titanic, 1997. And this makes sense, because if I want to know all the information about Pulp Fiction, you just get this data sequentially, right? You say, okay, start here, get out here, you know, pull this one page of data, right? And we basically, a lot of the information is information we need. However, with a transactional database, this does not make sense, right? Why? Because you're going to pull out these pages of information and you're going to throw away a good amount of it. We don't care about the title. We don't care about this title, right? We don't care about the production company. All we care about is these individual, half the data essentially, each time we pull it out. So instead, we move to column-based storage, all right? And this is the way Redshift stores stuff, this is the way Snowflake stores stuff, right? For analytical databases, instead what's stored sequentially is, you know, the titles are stored together, you know, in a page, and then this column will be stored together in a page, and this column will be stored together in a page. So why would we do that? Because then if I want to read just the year and the runtime, I can do that and just load these components into memory without loading the extra data into memory. Okay? So you know, when we work with analytical databases, underneath they're organizing the data in terms of the columns going together, right? There's going to be pointers, obviously, across, like we have to be able to associate that this was Pulp Fiction ultimately, but in terms of sequentially how the data is stored, it's stored a column at a time, okay? There's additional optimizations because this is one column at a time. You're able to compress this data because we know if it's a year, it's only 4 digits, and so there's only a certain amount of space that we need to take up in kind of like this string of data. So there are additional optimizations that you get by storing data in column because it's all the same type, whereas here, right, is different lengths of data stored. I think of it almost like in this strip, almost like a cassette tape of data. All right, so Redshift is a column-based database, but in general, analytical databases are column-based, and that comes from ultimately the types of queries that we typically issue to analytical databases are down through a column, whereas with an OLTP, they're across a row. Yes? Or no? Okay. The other thing to know about Redshift is that, and this is particular to Redshift, Snowflake operates differently, but this is the way Redshift operates. It divvies up your data. So this is a little small, but what you can see is we have like 2 movies here, Dark Knight and Inside Man. We have 2 movies here, Pulp Fiction, Titanic. You can imagine, really this would be like 1,000 or plus movies per each slice. There are 2 slices here, and there could be more, per node, where a node is a computer, right? And there are 2 slices here, and again, it could be more, where on this node, where a node is a computer. If we ask a question, right, like tell me all the revenue earned by a movie, or tell me the total amount of runtime, all right? How many minutes of runtime have we produced across all the movies? This is what will occur. We'll issue the query. We'll type it into our command line. It will go to the leader node. The leader node will then ask each slice of data to separately calculate, to sum up how many minutes per your slice. Okay, add them all up. How many minutes per your slice? Add them all up. How many minutes? How many minutes? Take these sums and then add them all together, right? And then it gets the total amount. So the advantage of this is that it's able to perform parallel processing, right? How many slices do you get? 1 per computer that you issue, so you can have a cluster of computers. And then for each computer, you get per the number of cores, right? So if you have 4 CPUs, each have 4 cores, you can partition this data into 16 slices, right? And then divvy them all up, and it can perform those queries simultaneously on each individual slice and then aggregate it. This pattern is called MapReduce, right? The mapping part is the individual summing it across X number of slices. The reducing part is then taking those results, those like sub calculations, and combining them, right? We did it with sum. It also works with average, right? Average, you can get the average each individually and then take a weighted average, right? If this was 10 rows and this was 1 row, right? This is only worth 1/10 the amount as the guy that's 10 rows. So you can do like a weighted average. You can do a lot of different things, and you get the benefit. Even a where clause works fine. Let's find just the movies by Miramax. Well, we issue that where clause across 4 different slices, and then we combine them. We combine the found results, right? So really, like any of our queries, we can, if you use something that has that capability, like Redshift, we can partition it across, and we can save a good amount of time by performing these queries in parallel. All right. So we have the leader node. The leader node is what directs the compute nodes. A leader node is just a computer, right? But it directs it. We takes in the command and issues this command to the compute node and says, hey, this is what to each our compute nodes or our worker nodes, and says this is what I want you to execute, and then each of these compute nodes will send back the results, and the leader node will give us the final tally. All right, and that's what Redshift is doing. So it both is column-based, and then it's also distributed computing that's able to perform calculations in parallel.
Jeff, I have a question.
Sure.
So 2 questions. So the column base. So this is the default behavior of Redshift. So any table which you create, it's going to create column base, right?
Right. I don't think it even can work differently.
Okay, and then second is your partition. So do you partition based on some specific key, or does it automatically slice these things?
It will, but it will do it by default for you. But you can partition based by specific keys. For example, and I'll probably have to. There are different ways to do that, like different strategies as to how to partition it. But for instance, say. So I probably don't want to. I probably would have to look that up. But it's based on like the query that you perform. Say you really care about data from a specific year, right? Well, then maybe we just have to. It can know. Okay, well, if I order this by year, I can just go to this one place to find the data. To find everything by that year. The other thought would be, well, let's spread it across years. That way we get in parallel. But I think what happens is that you want to combine, have the data go together based on how you're performing the query, because the combining of data oftentimes can take a long time. It's been a little while since I've taught that topic. But yeah, you can choose different strategies for partitioning the data. I probably should have to look it up before talking more about it.
Sure. So when you say leader node, so this, if you have only one EC2 but multiple cores, so same node can work as a leader node, right? Or do you have to have a separate?
I'm pretty sure it will do. Probably when we sign up for it, we can see. But I think that it might have to have a leader node. Actually, I think you can have just one node in Redshift. I'm pretty sure.
Okay.
Abhinav, do you know?
I don't.
Okay. Yeah, I'm not quite sure. Yeah, I'm not quite sure.
Thanks, Jeff.
For there was a collab you showed us with the diagram of data lakes.
Oh, yeah, let's talk about that.
Yeah, and so they address the processing layer versus the query layer. So the processing layer, they said, is where the MapReduce jobs happen. So I'm wondering, that was just logic entered as a SQL query, but it looks like you're saying there was a MapReduce job behind the scenes.
Let me
So
see.
it,
Yeah. Let's pull this up. So which part should I be looking at?
the processing layer, it says EMR is Elastic MapReduce, right? So we have Athena where we enter in a SQL query, and then we have EMR which does something. And if you looked at the Redshift diagram you just showed, it looked like they did EMR and the Athena layer equivalent at the same time. So if I were to enter in a SQL query on Athena, is it going to be doing some EMR protection in the background, or is it doing processing at the processing layer in the background, or when does the processing layer happen? You know?
Okay. Yeah. Let's talk through this. So processing, by the processing they mean the actual queries. All right. So here you can see they say, okay, well, Redshift with Spectrum. So this would count. Like when we issue a query to Redshift, that we are processing the data. When we do something like Athena, remember we have separation, right, of storage and processing. Because with Athena, we're storing the data in S3, and then we're processing it with the actual CPU in Athena. EMR, I guess that didn't make sense. So in other words, what I'm saying is this Redshift kind of is both storage and processing, right? Because we're storing the data. If you look at the this part, each one of these computers here has both the hard drive and the processor together, right? So what is Redshift used for? Let's go, is it here? Yeah, what is Redshift used for? Both storage, right? Actually, it holds our data, and also processing, right? Because we issue queries there. What is something like Athena? How is that used? Well, we don't really store data in Athena, right? Instead, we store data in S3. So here our storage and processing layers are more separated out. So this is, storage layer is S3, then processing is using something like either Glue, and we can talk about EMR in a second, or Athena, to query data from S3.
Yeah, so for example, like for the querying we do with glue, we would query in Athena and we would say, hey, query glue, right? So, and that glue had to run a single job beforehand. Is Athena doing additional, like what's the additional processing that Athena is doing versus the processing that glue was doing? Or,
Glue for us was like basically creating metadata about our S3 bucket, right? Kind of organizing it to like a table, saying these are the columns associated with it. And then what Athena was doing was issuing our query to say, okay, select all from limit to the first 3 rows.
but essentially all of the like compute and searching through everything was being done by Athena, right?
Yes.
And it would, so then when you talk about EMR, and maybe this is just confusing stuff, like it sounds like EMR is doing some of the actual logic. Like when you talk about the MapReduce before, right? It sounds like the MapReduce was kind of doing the actual work of Redshift. So how does Athena query EMR, or do they query
No,
EMR?
okay, these are different services. EMR, my understanding is this essentially would be like Spark, which we have not really spoken about, but it would be like, if you think about Athena is only operating on one computer, from my understanding, but EMR, you can see it's in the diagram too, you can use a cluster of computers to perform the query. So you could issue it, read data across multiple S3 buckets in parallel, and it can also process this data in parallel, probably even more importantly.
I guess my question is just like, does the EMR or the whatever, the MapReduce stuff, the PySpark stuff, is that like the last step typically, or is that just a way to pre-process stuff the same way Glue does?
This is the actual, so Glue we use for pre-processing, right? To like store the metadata, tell us what columns are there. This is actually performing, what we're talking about with MapReduce is actually performing the queries.
Okay,
Right?
thank you.
Yeah. Yeah, let's talk a little bit about this diagram. Okay. Right, so this is kind of saying, and this is the final kind of diagram about this lake house thing. So the first step is, all right, here's the different ways to get data, okay? So one is from our OLTP, right, like our transactional database that powers a website. Something like the CRM, right? Let's say that this maybe could be like Salesforce, right? Our customer relationship management service. And maybe this is, like I said, if it's Salesforce, like it's not even really touching our custom database. Salesforce is storing our data for us, but we can still probably move it in to something like Redshift, right? Because ultimately I may want to know, okay, like with my salespeople, which guys are talking to the customers that actually make me money at the end of the day, as opposed to maybe like I was like, I used to sign up just my friends for certain things when I was a salesperson, and they would never buy anything. So like you want to combine this data, right? Then you have like the SaaS applications, right? It's like other similar types of things like HubSpot or Mixpanel. These are off-the-shelf tools you could use lots of times for marketing, but again, you want to pull in that data. Here maybe you're scraping data, something like that. And then finally, we talked about like social stuff, right? Like Twitter type of data, or Facebook. How many people are posting about our products? Now, how do we read in that data? Okay, so the data migration service, there are different options. One that we'll be working with right soon is Airflow, right? Which like every day, like let's pull the data from our OLTP and move it into Redshift, right? This is like batch-based, I guess movement or ETL of our data. The other thing, this is used for streaming data. We kind of talked about like transaction, like very fast transactions. For example, like maybe we really care if we're like financial firm about like some fraud that could occur, or like, okay, someone's trying to, if it's Facebook, people keep re-entering the same password and now we want to lock them out, right? So, you can, we may have to take that, batch wouldn't be fast enough for us, right? Because it's only happening every day or every minute or every hour. We need to shut it down pretty quickly. So for that, you could use like streaming data to then perhaps kick off, say, some sort of Lambda job to take some sort of action when you see, certain behavior occurring. So this is like what they're talking about here is the ingestion layer. We're not really working with streaming data here, but you can imagine, each event that you're storing. Here, right, we are working a lot with this, and we're using something like Airflow generally to move it in. We also saw how we could schedule stuff with like EventBridge, and you could potentially use that as data migration as well. But most people we can talk about later. We'll use something like Airflow. Okay, so now we actually get to storing the data, right? So this is the data sources. This is moving data from our data sources into our what they call like this lakehouse. Now there are two options, right, in terms of storing the data. One is like unstructured or like blob-based storage. So that we saw could be like the CSV files. You may also say you're scraping a website every day, and you might want to store the raw HTML. You probably do, because say you're only pulling out with our like Indeed data, right? Say we're only pulling out like the company name, but we're not pulling out the rating. And then at a later point in time, we want the ratings. So we want to hold on to that HTML data in case we ever change our mind, right? So this could store both like more structured data, or what they'll call semi-structured data, like CSV, JSON data, as well as unstructured data like PDF, emails, HTML, right? Data, we'll actually want to derive data from that. Redshift is structured, right? This is like Postgres, okay? So this is a relational database where we are, have to put in the work to format the data, right? If it's originally in HTML, we can't just store it there. We have to pull out the data and organize it to then store into tables. Now, if I'm like a data scientist or a data engineer and I want to query this data, I may want to get requests from Redshift, or maybe some of the data is stored in S3. In order to keep track of the various data sources, we saw briefly this thing of like lake formation, which will say, okay, like here's a table, right? In fact, it's really an S3 bucket, but it calls it a table in this database, right? And have multiple S3 buckets living inside of there, right? So lake formation is a way of like cataloging this data the same way it might live inside a database, and we can search, do /L to see different databases. Here we can also see, hey, these are the different data sources that you have available. Some are Redshift, some are in S3. Before moving on to like other layers, let's just talk about why S3 versus Redshift. S3 is cheaper, right? It's just storage. So it's going to be a lot cheaper, way cheaper than something like paying for Redshift. So why not just store everything in S3? Well, one, it's more costly. It's not more costly. It's generally, does not enforce any degree of structure. It's not relational really. So, performing something like joins are going to take even more time. And, because we do not enforce like structure on it, this kind of data lake idea, that's what people, when they're just talking about S3, they say like data lake, that can turn into like this data swamp, because it's so cheap, to store data, we can just throw anything in there and not format it, and therefore it becomes kind of like unusable, right? We don't know what's there, and it's not processed for us. Redshift, we are processing the data, but one, it's more expensive to like run this, to keep this thing up and running, and two, right, just we have to perform transformations to actually store and associate the data in relational databases. So this is like the trade-off that you work with, right? And then also in terms of skill set, right, like we're pretty technical at this point. Data scientists are fairly technical. They can query data from S3 using something like PySpark, or maybe like Athena, or etc., or even like Pandas, but you would not expect like an analyst to be able to know Pandas or one of those tools. So this might be more accessible because a lot more people know SQL than know Python and know those other data sources. So you can think of this as being more for like data scientists, technical people, and Redshift or other analytics services hooking into something for our just data analysts, marketing analysts, business analysts, things like that. All right. So what they're proposing here is have a combination, right? Like less structured data more for data. Some data science people may want to hold on to additional data. They don't know what they're going to extract. So we want to hold on to this data, but we also want more structured data for like our analysts here. And that's this idea of like the lake house. And so lake formation is a way to, allow us to have both data sources and then also keep track of both of them. All right. And this is just storing metadata, right? Like this is an available S3 bucket, and here are some tables in Redshift. Now the processing, right? This is actually performing the queries to the data, and you can see like Redshift is combining processing with storage, okay? Because, and we saw that in our part here, right? We both were the data is actually stored on the computers, and we have like a CPU that is performing the query. With something like Athena, that's not the case. We're storing the data in S3 buckets. These things are dumb. There's no CPU powered to them. However, we can query them. We can query our S3 buckets. How would you query it? Athena was one option. Another option for querying your bucket is to use something like PySpark, right? PySpark, we haven't spoken about it yet, but you can read data directly into memory from S3, and that data can be partitioned. Maybe I'll talk about this later. The data can be partitioned instead across disks, partitioned across memory stores, right? So the only data is read from S3 directly into memory, and then you can issue parallel queries in memory, all right? And then when you're done with the query, it just still lives in S3, and you shut down your cluster. All right, so that it's just another way to read data from S3, but you can partition that data in memory into different slices to perform MapReduce in memory through PySpark, or that's what we can do. Anyway, we can talk about that later, but for right now, the purpose is that it's another way to read data from S3. It's something like this EMR PySpark thing. And then finally, the consumption layer is, well, who actually sees the data and does something with it? And that's, this QuickSight is their dashboarding tool. SageMaker is kind of like Jupyter Notebook. It does more than that, but you can kind of present some reports from there. Or somebody can just actually make queries with it and see the results and do it from Spectrum as well. From Redshift as well. All right, that was a mouthful, but you can start to see hopefully that's helping you make sense of this thing. We have the various sources that we're reading data in from, right? We have to have a way to move that data into our database, right? Into an analytics database, whether it's Redshift or storing our data in S3. We have to have a way to query that data now that we're storing it. With Redshift, that's combined with S3, and we will need another tool to do the processing, whether it's something for us like Athena or PySpark to read from S3. And then finally, we want people to who's the end person viewing this data or acting on this data. It could be dashboards. It could be us just seeing the queries. It could be like a Jupyter Notebook type of thing. All right, and this is Amazon saying to use all of its tools, right? If we showed a picture from Snowflake, it might be different, but this isn't bad, right? This is, I think, does a pretty good job of breaking this down.
Jeff, one quick question on this slide.
Mm-hmm.
So in this you're saying lake formation common catalog. So Amazon provides some sort of service where you can do the lake formation, you can catalog.
Yeah, and we saw that, by the way, right? When we
I'm just going through some other things.
Sure. Sorry, I'll pull it back. Yeah.
Yeah. So what it means is your consumption layer or your processing layer is going to interact with lake formation, not with Redshift or S3, right? That is going to be embedded.
I don't know totally, because when we process, right, these things aren't as cleanly segmented, right, as the diagram displays it. Here, it's all combined, right? But let's say you want to see what's all the data sources I have available to me. You would go to lake formation, because that would combine, that would show you both of these. But if I want to actually issue a request to Redshift, you'd have to log into Redshift or connect directly to Redshift, not, from my understanding, through lake formation. You can cross this off and still issue queries, just with Redshift. Yeah. So this is more like I said, I like this word common catalog. This is more, okay, show me a list of all the tables I have access to. Some of them are stored in Redshift. Some of them are more like these S3 buckets. So if I'm a data scientist, Lake Formation provides like a service, or data engineer. Lake Formation tells me, okay, here's here's a catalog, right? Here's a schema of the data sources living in different storage units, whether S3 or Redshift.
So then this is more of a documentation layer.
Yeah,
where we
metadata. Yeah, I would say so.
So is that like DBT in some cases?
No, DBT is even different. DBT is once I store the data into a data warehouse like Redshift, I'm going to want to coerce it, change it from this OLTP format to OLAP. And so far we're doing this, I guess, before it even enters Redshift. But I think more typical now is that people will first just directly move your OLTP data into Redshift and then use DBT to coerce the data with SQL into this data mart OLAP format. So we'll get to DBT, but no, it's more of a tool to coerce the data once it's already in your analytics database.
And is there another concept called Delta Lake? What is that?
I don't know. That's
Okay.
yeah, I don't know. I think that's like a tool that Databricks has maybe, but it's probably some sort of concept that lives on top that
Sure.
is incorporated. But yeah, this is the idea is, right, okay, well, we have this data warehouse, we have this data lake, we can, use both of them, right? Use, less structured data, more difficult to query, more structured data, but more costly, right? Easier to query, and use both of them, right? Cool.
And Jeff, are we going to have some sort of exercise where we are going to touch upon all these tools?
So this we kind of use, so the S3, like the data lake format, we kind of saw, right, with our last section, right, where we're querying data, storing it in CS, querying data, storing it in our S3 buckets, and then, querying it with Athena, right? Like we saw how we can do that. And now we're also adding in Redshift, right? So this is why I bring this up here, is like the last unit was kind of this data lake type format, right, where we're using this less structured data, querying it from S3, and now we're moving into this Redshift format where this is going to be more structured, also more costly, right, because it's combining processing with storage. All right. So, in terms of what's for you all to do, I'll deploy basically the readings. Goes through this. And then I'll let you move into Redshift and start pulling data from S3 into Redshift. One thing I'm not going to talk about it now, but one thing I did not talk about was like staging. Right, remember the format that we're following essentially is take our data from our transactional database, move it first into S3, right, blob storage, and then move it into like Redshift. Okay, and this is our staging. This is, you can think of this as our staging layer. This is falling a little, I think, like there's less reason for a staging layer now than there used to be. But reasons why you still might want a staging layer is one, it can hold on to like this historical like snapshot of data. So for instance, like say a user changes their phone number or whatever, right? Like, and you update it in your database. And so then you update it in your Redshift, right? You've lost their old phone number, right? Like it's just nowhere. Whereas staging, we can hold it, store it in S3 buckets, have this, we can go find it somewhere and pull back that data. And then the other thing is maybe you just say for like really unprocessed data, let's say all we have is like OLTP and we have our data warehouse, and say we're scraping data from HTML. Here, I guess it's acting more kind of like a data lake. You want to store that HTML somewhere. Like we said, you might want to go back, get the rating, right? So staging can be used as a way to just like cheaply hold on to data that you might want to use, yet you don't yet see a use case for it in your data warehouse, or there's just some amount of data loss that can occur because data changes, and so as you update your data warehouse, you've lost it, like that, that old phone number, that old address of the user. Okay, and so S3 is just like cheap enough that maybe it's worth holding on to that data. Okay, so the idea is, okay, we have this data. First, we'll store it in S3, and then we'll move it over to our analytics database like Redshift. All right, so that's the format we're following for now.
So in this picture, we are missing the ingestion layer, right?
Well, this would be the ingest. This would be our first. This would be our raw data.
Yeah, but
and
we are not storing any metadata, right?
Well, yeah. I mean, here you would have, as long as we're just using Redshift for now, right? Like this will have like your data source. You can just explore it like Postgres and see your various databases or tables. /pt to see the table, /l, right, to see the list of databases. Yeah, we're not using the lakehouse thing. Like we're not storing data. We're not storing the metadata because I guess the idea is not that we are. It's almost like a separate unit. Like we're not saying, okay, we also have this data lake where we're keeping track of data as well as this data warehouse. If we did, then we would. We would store that information in some sort of metadata layer. Yeah.
Jeff, in typical staging, ETL layer, staging area is supposed to be temporary, where you do the transform after that you do the transformation and push it.
Yeah, but I think so. People do it different ways. I think there's less of a use case. For traditionally, people would like perform the transformation, like store the data here, then perform some transformation on the data, and then ultimately move that into the data warehouse. Now that pattern has fallen out of fashion, where instead what you do is you just store the data, the raw kind of like data that you're ultimately working with, in the data warehouse, and then you'll transform that data, and this will just be in one schema called like raw. And then you'll keep transforming that data until you finally get to this OLAP format. And you'll just perform those transformations in the data warehouse. So like, yeah, so so it's like, so in this world where the transformations are performed in the data warehouse, what is the purpose of staging? And I think there's less of a reason for it, but two reasons for it is one, store, this historical snapshot of data, and two, data that we just simply can, like emails or HTML that we simply cannot place really in a structured data warehouse that you can store in S3 buckets. All right?
Yeah, but then when you say historical snapshot of data, then it will become huge. I mean,
it'll be huge, but it might be worth. I mean, yeah. So there's ways you can pay for even cheaper than S3 storage in AWS. Yeah,
okay.
It's like called Glacier storage or stuff like that. There's always a way. All right, I'm gonna call that for now.